Hey guys. In the last couple of sections, we went over brute force graphing techniques, what it is to be a linear equation, um, things like that. So in this next section, we're gonna discuss x and y intercepts, which is something related to the graphs. And understanding those is going to help you to graph things more efficiently, so we don't really have to use the brute force methods that we used in the last couple of sections. So first of all, let's just start by discussing what an intercept is. So on any graph, an x-intercept is where the line crosses the x-axis. Right? The x-intercept is where the line crosses the x-axis. So in this little example below here, this one that I'm highlighting in yellow, this is the x-intercept because this is where the graph, the red line, crosses the x-axis. Right? And so you see I have labeled here x-intercept, x-int for short, equals the point 50. All right, so the y-intercept is where the graph crosses the y-axis. I've highlighted that in green right up here. Right? And so you can see this is where the red line intersects the vertical axis. That's what's called the y-intercept. That point is 0, 4. Right? That means x is equal to 0 on the left side, y is equal to 4. For the x-intercept, y is equal to 5, but x is equal to, x is equal to 5, but y is equal to 0, right? Because this is the way that we make our pairs, x, y, x, y. Okay, so that's what the y and x intercept look like. Unless we're using a horizontal or vertical line, all linear graphs will have both a y and an x-intercept. So you can see these are two examples of first a horizontal line. You can see this one. This is the line y equals 3. You can see this only has a y-intercept because it's horizontal, so it goes in both directions without ever crossing the x-intercept. The y-intercept for this is the point x equals 0 and y equals 3. Similarly, a vertical line like we have over here on the right side, this is the line corresponding to the equation x equals -4. Vertical line only has an x-intercept. You can see that x-intercept happens when x equals -4 and y equals 0. So one thing you may have noticed above is that the y-intercepts are always in the form 0a, where a is some number on the y-axis. So let's go back and look to that. So this horizontal line produced the number 0, 3, because x is equal to 0 there, right? The y-axis, or the y-intercept up here that I've got highlighted in green, this is 0, 4. Because the x-coordinate is equal to 0 and the y-coordinate is equal to 4 at that point. So you may have noticed that. That's always going to be true if we have a y-intercept. That's because any point on the y-axis has to have an x-coordinate of 0, right? And if you just think of how we find our points, right? If I say over here on this right side example, find me the point 0, 3, right? I say, okay. First, I adjust on the horizontal axis, the x-axis, to the point 0, which is right here at the origin, and then it says I go up 3 units, which is right here. Right, and so anything along this vertical axis, sorry, just pretend this line is right on the vertical axis, anything along this vertical axis, x is always going to equal 0. Excuse me. Okay, so from that, it basically follows that the x-intercept is always of the form b, 0, right, where b indicates the horizontal location on the axis, right? And so I'll mess with this one over on the left side here. So obviously, like if we have the point, suppose this point over here were our x-intercept, the point 3, 0. right? Since the point is directly on the x-axis, right, what does y equal there? Y always equals 0 when it's on the x-axis, and so all x-intercept points will have the form 3, 0, right? So y-intercept is of the form 0, a. X-intercept is of the form b, 0. Something really important to note here. It happens so often, it's crazy, and I used to do this myself, so I know why we have that urge to just say the y-intercept is equal to a single number, but we can't do that because the y-intercept is actually a point on the plane, right? If you say y-intercept equals 5, like I've done in this example I've highlighted in red, that doesn't make any sense. Right? You have to give a point in the plane. The y-intercept happens at 0, 5, that point in the plane, right? And so it is incorrect to say the y-intercept equals a single number. It has to equal an ordered pair. The same is true of the x-intercept, right? You can see here, if I say x-intercept equals -11, that doesn't actually make any sense. I have to say x-intercept equals the point -11, 0, because that tells me where it is in the plane. So for this example, we're asked to give the coordinates of all the x-intercepts and the y-intercepts from this graph below. We're not going to deal with any graphs that look like this in this class. This is a nonlinear graph because it's not a straight line. And this is the graph of, just in case you're wondering, this is the graph of y equals -x² plus 4. That's something that you'll be dealing with in 105 and pre-calculus. But for this class, we only deal with linear ones, except for in this example, of course. So let's go ahead and zoom in and figure out where all these y and x intercepts are. So my y-intercepts happen when my graph crosses the y-axis. That only happens here. So I'm going to go ahead and I'm going to just go ahead and circle my x-axes, my x-intercepts as well. Right? So where do I cross the x-axis? Right here and right here. So here's the proper way to identify these. I'm going to say y-int equals the ordered pair 0, 4. Because the y-coordinate up here is 4, and all along the y-axis, the x-coordinate is always 0. So now for the other two, right, I'm going to say x-ints equals, I'll do the one on this side first. So the x-coordinate here is equal to a -2, and of course, if we're on the x-axis, the y-coordinate is equal to 0. Now we're going to say or the x-intercept, or we could say and. Actually, we should say and, because they're both true. And the other one over here on this right side, my x-coordinate is 2, and my y-coordinate is 0. So this is the full list of x and y intercepts for this equation, for this graph, I should say. All right, so that's really all you need to do to find the x and y intercepts, right? You just identify the point where they cross, and then you list it. That's it. Easy peasy. All right, so let me zoom out here. All right, so let's go ahead and learn how do we use these intercepts to graph things. So first of all, how do we find the intercepts from an equation, right? And so the last thing we did was we looked at a graph and we identified the intercepts. Well, that's easy enough. But what do we do when they ask us to find the intercepts to a specific equation? So let's see now. For this next example, they give us 2x plus 4y equals 20. Right? If I asked you to find the x and y intercepts of this, you'd tell me, what? How do I do that? Right? Well, you graph it for me first, and then I'll find those. But we don't need to graph it. All we need to do is remember the nature of x and y intercepts. So we just need to remember that at the y-intercept, x is always equal to 0. And at the x-intercept, y is always equal to 0. Those are the two things that we have to remember to find the x and y intercepts for this problem. So in the book on page 174, they give you step-by-step instructions for this, or, well, just instructions. They're not really step-by-step. So basically, it says right here, to find the y-intercept of an equation's graph, we replace x with 0 and solve for y. And of course, to find the x-intercept of an equation's graph, we replace y with 0 and solve for x. All right, so let's go through that and do that. So the first one says, to find the y-intercept, we replace x with 0 and solve for y. All right, so we're going to say this is our y-int calculation. All right, so I have 2x plus 4y equals 20. This says my instructions are replace x with 0 and solve for y. So if x is equal to 0, this entire 2x out here in front just goes away, right? Because 2 times 0 is 0. So now I only have 4y equals 20. Now I'm going to divide both sides by 4, just like I usually would, which gives me y equals 20 over 4, which is actually equal to 5. But we're not done. So all we did was find the y-coordinate of the y-intercept. Now we have to fully state our y-intercept. I'm going to do that over here. So I'm going to say y-int is equal to the point x equals 0, y equals 5. And this is my full answer, right? If I don't give this ordered pair, that's not a full answer, right? If I give this answer over here, just y equals 5, I'm not going to get full points from that because that doesn't actually make any sense in the plane, right? That's a full line, right? We want a point. Okay. So that's how to find the y-intercept, and I haven't given myself enough room here, so let me just move my y-intercept over. I can find the x-intercept on the other side. So we have y-int is equal to the point 0, 5. All right, let's do our x-int on the other side. X-int. These are our calculations. So once again, I have 2x plus 4y equals 20. I'm going to go up and look at my instructions. My instructions say to find the x-int of an equation's graph, we replace y with 0 and solve for x. Okay, so that means the 2x remains, but the 4x actually goes away, because if y is equal to 0, the whole thing is equal to 0. So I just have 2x equals 20. I can divide both sides by 2 to isolate my x, and I have x equals 20 over 2 is 10. But I'm not totally done. I don't want to make that mistake of just saying the x-int is x equals 10, because that doesn't make sense. I'm going to list it down here. X-int is equal to the point, right? X equals 10, y equals 0. I'm going to draw a little box around it to make sure that my instructor knows that that is my final answer. I'm going to erase this other box to prevent confusion. Okay, so that's it. That's how you find the y-int and the x-int of any equation like this, right? To find the y-int, set x equal to 0. To find the x-int, set y equal to 0. That's it. Okay, so now I'm going to show you why this makes this kind of stuff a little easier. But first, I'm going to pause it and adjust my graph. Okay, so I noticed that my x-int was way over here at x equals 10, so I just had to add some extra numbers on this side. Okay, let's go over how this is easily used to graph things, right? And this isn't the easiest graphing method yet. This is just an easier one than brute force. So first, we're going to plot the y-int. Doesn't matter which one you plot first. I'm just plotting that first because it's there. So here we go. And I'm going to label this point. You should always label your y-intercept and your x-intercepts. Okay, so this is the point 0, 5, my y-int. Now I'm going to label my x-intercept. That is the point 10, 0. That's way over here at x equals 10, y equals 0. I'm going to label this 10, 0. Okay, now to graph this line, all I need to do is connect these 2 points. right? And so let's see if I can do this without making the line look totally terrible. Hey, that's not bad. All right, so that's it. That's all I would need to graph that, and just pretend that this actually intersects right at 5 up here. Just have to use your imagination for that one. So that's basically what this graph would look like. So now maybe we should just go ahead and find another point on this graph and check to see if this is valid, right? That's what we mean by this last line. Find a third point, and this should say and check, and check. Okay, so we find a third point and we check. Let's see now. The point that I think we should probably try and find, let's go with, how about 2? And I'm only saying 2 just because, I don't know, it looks like with 2 I can get a very close estimate here. And so now we're about to pick a point on this line and see what its coordinates are, right? And so I'm going to go up from 2, I'm going to draw a straight dotted line, and this isn't going to work very well because I mashed all these little numbers in over here together. If this graph were evenly spaced, this would work far better. So I think 2 corresponds with 4 for this particular graph. So what I'm going to go ahead and do is check to make sure this point is on that graph. So I'm looking at the point 2, 4. And I want to know if it's a solution to this graph. So we're going to make our little table that we're so used to making. All right, so we have 2x plus, whoops, I think it's 4y equals 20. All right, we're going to draw our little table. Cha-ching, cha-ching. And what's our point? 2, 4. We're going to test the point 2, 4. All right, remember this is x, y. So I'm going to replace all my x's with 2's. So this is 2 times 2 now instead of 2 times x. I'm going to replace my y's with 4's. So this is 4 times 4 now instead of 4 times y. And then there's nothing really to do on the other side, so I'm just going to carry the 20 down. All right, now I'm going to start doing my math. 2 times 2 is equal to 4. 4 times 4 is equal to 16. And we can already see that this is going to turn out good, right? And so I am reaching a point where I have 20 equals 20. This is a true statement, so this is a solution to this equation, right? If we reached the statement that was not true in the end here, we would not have a solution to this equation. So we've checked a third point on this line to make sure that the equation is valid, and it turns out it is. Now this third point method is a little bit, it's not as consistent as you'd like it to be because it relies on the exactness of your graphing. And I don't know about you guys, but my graphs are never exact, which doesn't mean you shouldn't strive for that. That just means it's not a reality to expect that to happen all the time. So be careful with this checking points method from visually like graphing things. We're going to come up with some better checking methods later on. But for now, that's how you find a third point and check, right? You could always reverse engineer this and just do a little, I guess a better way to do this even would be to find a third point by choosing an x value, finding its corresponding y value, and seeing if that's on the line. So what do I mean by that? Let's do that over on the right side here. So I'm going to set up my other kind of table, right? This is my brute force table. This is the table where I find pairs to plot. And so what I could do is I could just say, we'll use the same points. We'll just say, actually, no, we shouldn't use the same points. How about let's use 4. We'll suppose x was equal to 4. Right? Then my equation, 2x plus, oops, maybe I should write it up here. Just so you guys know, this isn't really how you should organize your papers. It should be much more organized than this. So I have 2x plus 4y equals 20. If x is equal to 4, this 2x turns into an 8 plus 4y equals 20. And then I have 4y equaling, if I subtract 8 from both sides up here, then I get 4y equals 12, and y equals 3 if I divide both sides by 4. So I have 4, 3. That means one of my pairs should be 4, 3. Let's see if that's roughly where the graph ends up at. Okay, so I have my point over here. I'll do this one in green. So I have my point x equals 4 right here. If I follow it up to my graph line, I reach the graph line, and see, so this one is not so exact. Right, this one is not so exact. We end up at like 2.5 over here on the y-axis, and so this point was a little less accurate than the other one. But you can see it's in the general area, which means it's probably correct. So those are the two not super bomb-proof ways to check your work on these. All right, let's go ahead and use intercepts again to graph this function, the function 3x minus 2y equals 60. So right off the bat, we're going to calculate the y-intercept. So I'm going to say y-int. These are my calculations for y-int. So I have 3x minus 2y equals 60. Now remember, to find the y-intercept, we set x equal to 0, then we solve for y. Okay, so if x is equal to 0, then 3x goes away, because 3 times 0 is 0. And I just have negative 2y equaling 60. Now I divide both sides by a negative 2. And this gives me y equals 60 over negative 2 is negative 30, right? And so my y-int, maybe I will just list it over here. My actual y-int is the point 0, comma, negative 30. Whoops. 0, comma, negative 30. And I can already tell, just looking at my graph that I've copied in here, that I'm going to need to adjust. I'm going to need to scale my axes a little bit, because my axes only go to 5 in each direction. Negative 30, that's just not going to cover it. So now, I found my y-int. Go ahead and compartmentalize here. Now let's find our x-int. So I have x-int. These are my calculations for my x-int. 3x minus 2y equals 60. So remember, to find the x-intercept, we just set y equal to 0 and then solve for x. So negative 2 times 0 is 0, and I have 3x equals 60. If I divide both sides by the coefficient on x, I end up with x equals 60 over 3, which if you calculate it is just 20. All right, so now I'm going to fully list my x-int, right? I'm just going to list it up here so I have them next to each other. X-int is equal to the point 20, comma 0. I'm definitely going to have to scale these axes. And actually, since they're both in units of even tens, right? And since my axis already has my whole numbers, I'm just going to add some zeros here, right? We're going to turn this into 20, and this is totally fine to do, right? You scale your axes as appropriate. You know, if you started out 0 to 5 and you find you need to graph to 30, you may need to redo everything or just add a little 0 on there. But you know, if it says your y-int is at 0 to 30, don't try and extend your axes to reach 30 by ones, because that's not going to work out very well. All right, so now we've adjusted our scale on our axis so that we can see this whole thing. I'm going to do this in red. So first, I'm going to plot the y-intercept, which is at 0, negative 30. So I have 0 on the x-axis, which is at the origin, and then I go down to the point negative 30 on my y-axis. Then I'm going to draw a little arrow, and I'm going to label this 0, negative 30. All right, so now I'm going to find my x-intercept, which is at the point 20, 0. So I go over 20 on the x-intercept. It's a positive 20, so I go over to the right, and then 0 on the y-axis. So this little point is the point 20, 0. All right, now all I need to do is connect these 2 points with a straight line. See if I can get this exact here. I really can't though. So just pretend this line goes directly through those 2 points. Okay, so this does ask us to find a third point as a check, so we're going to go ahead and do that. I'm going to do that below here. Compartmentalize my stuff again here. So to find a third point, we just create our little tables, right? X, Y, X, Y. All right, what's a good point? I don't know. I'm looking at this and I don't know, 30 looks like a pretty solid point. Let's go ahead and calculate x equals 30. And I'm gonna choose large numbers like this because my graph is in a large scale. If I chose x equals 2, it'd be really hard to see if that was accurate, right? Because 2 is way zoomed in here. I choose x equals 30 because that's roughly the scale that the graph is in. I should get a little bit better accuracy doing that. So if my x is equal to 30, then I have 3x minus 2y equals 60. If my x is equal to 30, then I have 3 times 30 over here. That's going to give me 90 instead of 3x. Then I have negative 2y equals 60. Okay, so the 90 is positive. It's attached through addition or subtraction. So I'm gonna add its opposite, right? Since it's positive, I'm subtracting 90 from both sides. Negative 90, negative 90. These guys go to 0. I have negative 2y equals 60 minus 90. That gives me negative 30. Okay, divide both sides by the full coefficient of y, right? We're doing division now because the negative 2 is attached to the y by multiplication. All right, so divide both sides by negative 2. These guys cancel. Right, I see that this is 30 over 2, which is equal to 15. I'm also going to notice that I have 2 negatives, which are going to cancel each other out and make a positive. So 30 over 2, that gives me a positive 15. So 30 corresponds to 15, and the point we're looking for is 30, 15. So let's do a quick check. Okay, so we have the point 30 right here on the x-axis. Let's just trace our line up to the actual graph, and then from there we trace over to our y-axis. Is that 15? I would say it's pretty darn close. You know, probably a little bit off, but I think that's close enough to say, yeah, we got this one right. We are correct. So that's basically it to find your x-intercept and your y-intercept on a graph. You'll definitely want to organize your problems a little bit better than I have. You know, just for the purposes of explaining all this stuff, I tend to write a lot more than is necessary. But yeah, you should probably kind of organize it like this. Put your graph on one side, do your calculations on the other, clearly identify what you've found from your calculations, and then go ahead and put them into the graph. All right, so the next dealio, we'll be talking about graphing horizontal or vertical lines. So we've already discussed this a little bit. Let's go ahead and discuss it officially. So far we've graphed a lot of equations that look like this. Y equals x minus 1, or 2y plus 4x equals 54, or something involving both x and y. Sometimes, though, there's only one variable, right? Sometimes they ask you to graph y equals 3, or x equals 4, or y equals negative 22. When they ask you to do that, it's always going to be either a horizontal or vertical line. For the first example, we're going to do a horizontal line. So the graph y equals 3. Right? If we were doing this on a number line, if we were doing this on a vertical number line, we'd just put a dot on 3. But we have 2 number lines to think about. And so what this equation is asking us, or telling us to graph, it's saying, show us all the points where this equation is true, right? Where y equals 3. So just real quick, let's talk about what this point is equal to, right? And so this point, right, at its intercept, we know it's going to be at least there. This is the point 0, 3. 3. Maybe I'll erase that. 0, 3, right? And these points are always organized like this, x, y, right? So x is equal to 0, y is equal to 3. Since y is equal to 3, this makes this equation true. What about this point over here? What if x were equal to 3 and then I went up to y equals 3? So this is the point 3, 3. So x is equal to 3, but y is still equal to 3, which means this equation is true at this point, right? Because y is equal to 3. And in fact, any point where y is equal to 3, that's going to make this equation true. It doesn't really matter what the x value is. So even if we came all the way over here to x equals -5, traced our way up to y equals 3, right? This is the point -5, 3. This is also a true, this ordered pair makes this equation true, because it doesn't matter what x is. As long as y is 3, this is true. So that's why this corresponds with a horizontal line at y equals 3. And just pretend this is like horizontal and straight. All right? Because every single point on this line, y is equal to 3. So this equation is always true. For the same reason, that's why we graph x equals -4 in a vertical line, right? Because x equals -4 here, so that point, if we have the point -4, 0, this equation is true because x equals -4. On that same vein, the point over here, which is -4, 2, this equation is still true because x is still equal to -4. That's why we draw a vertical line at the point -4. Right, because any point along this line is going to be true, right? Even way down here, as we just keep going far, far down, the point -4, negative, 1,000, 10,000, that's still true. As long as x is equal to -4, the equation's true. That's why we draw a vertical line down to infinity. So when we have x equals a single number, it's a vertical line. When we have y equals a single number, it's a horizontal line. All right? Here is the official version of that. Right? This says that the graph of y equals b is a horizontal line with the y-intercept 0b. And likewise, the graph of x equals a is a vertical line with x-intercept a0. Here's an example where they ask us to write an equation for each graph. So all we need to do is notice that this is a horizontal line for part A here. Right, so this is an x equals something equation. So we just need to find where that horizontal line lies. So it looks like we have a -3 down here, -1 up here. This is -2. So x equals -2 is the graph of this horizontal line. All right, so part B, this is a vertical line. So this is going to be a y equals something problem. All we need to do is identify what that y point is. Well, it's one tick over from 0, so this is a y equals 1 line. That's it. That's how we identify what the graphs of these are. All right, so that was 3.3. That was a lot of stuff about x and y intercepts, graphing, things like that. On the next exam, I'm definitely going to have you label x and y intercepts a lot. You'll probably get some problem involving a horizontal or vertical line. I'm going to be asking you to use different graphing techniques. So, this is a fairly important section. So make sure that you know this stuff. That being said, let's go through to rates of change. Graphing in this class is a lot about rates of change, right? And the steepness of a graph tells us about that rate of change. Because we're using two axes, right, we can view how two quantities change in relation to each other. And so this is what we call a rate. Right? A rate is a ratio that indicates how two quantities change with respect to each other. So as you can see over here on the left side, the steepness of this line is not very high. So this rate is a little bit lower, right? However, this one on the right side, this is a very steep line. That means the rate is higher, right? And so these two rates are different by the steepness of their line. What are examples of rates? So probably one of the most common ones is a car driving a certain number of miles per hour, 30 miles per hour, that's a rate. A worker that makes $15 per hour, that's a rate. You're making $15 per hour. If you only made $10 per hour, that would be your rate. A copy machine makes 22 copies per minute. Right? You can see the units don't need to be in hours. They just need to be specified. A class of 20 if a class of 25 students pays a total of $93.75 to visit a museum, if you divide 93.75 by 25, you get $3.75 per student. So just keep in mind here, all these rates have two types of quantities in question, right? For this one, it's distance and time, right? And so when we take a graph of this, we're looking at the visual representation of distance over a certain time interval. With this one, it's dollars and time. With the copy machine, it is copies and time. With this last one, it's money per student, right? And so this doesn't have to be like a per minute or per hour kind of thing. It could be a per student or per whatever. So just like I said before, these rates represent the steepness of a related graph. And so a graph of 30 miles per hour, let's just kind of do a distance one here. So there's 1, 2 hours, and we'll say this is 30, 60, 90, right? And so if we were at 30 miles per hour, this would be our distance function if hours were at the bottom. And so after 1 hour, we'd be at 30 miles. After 2 hours, we'd be at 60 miles, right? And so this would be the graph, roughly, of like we'll say y equals 30 over 1x. But if we want a different rate, if we want, let's say, y equals 60 over 1x, right, for 60 miles per hour, what we want to, we're actually going to end up, after the first hour, we're going to end up all the way at 60 miles, right? I'll make another 120 up here. For the second hour, we're going to be all the way at 120 miles, right? And so when we graph these two, our distance graph, right, the higher rate corresponded to a higher steepness in the graph. All right. Oops, I put my examples too close. Just a second, let me space these out. All right, so let's dig into our first example here. So this is all about car rentals. Let's go ahead and read through and highlight any important stuff. So on January 3rd, Alicia rented a Chevy Cruze with a full tank of gas and 9,312 miles on the odometer. On January 7th, she returned the car with 9,630 miles on the odometer. If the rental agency charged Alicia $108 for the rental and needed 12 gallons of gas to fill up the gas tank, find the following rates. Okay, so rate A. They want us to find the car's rate of gas mileage in miles per gallon. So what we want is miles per gallon, right? Gas mileage in miles per gallon. So we want, for A, we want it in miles per gallon. This is the G. Okay, so first of all, we need to calculate the miles, right? So how many miles did she drive? So she started out with 9,312, ended up with 9,630. So this is 9,630 minus 9,312, excuse me. So go ahead and do our math on this. And this gives us 318 miles, okay? Miles. Now, they want this in per gallon. So we just need to recognize that she had 12 gallons of gas. So now that we have both those quantities, we know that we want miles in the numerator, gallons in the denominator. We just need to throw them in there. So we have 318 miles over 12 gallons. So for that, stay with me while I find my calculator. Okay, so for that rate, this is equal to 26.5 miles per 1 gallon. Right, and so it's important to keep that per 1 gallon in the denominator there, even though it's just a 1. That just tells us sort of the relationship of the two. So part B. Part B, they ask us for the average cost of the rental in dollars per day. So this is the way they want us to set this up. Dollars over days. Right, that's what the per kind of means. All right, so first of all, let's calculate the dollars. The dollars, we don't need to calculate it. They just told it to us. The dollars were 108. 108. The days, well, let's see now. She rented it on January 3rd. She got it back on the 7th. 7 minus 3 is 4. So she had it for 4 days. Now we just need to do the division. So 108 divided by 4, that gives us 27. So we have $27 per 1 day. That is the rate that she was charged. Let's do the third rate. Rate C. What do they want? They want the car's average rate of travel in miles per day. Miles per day. So they want miles over days. So we already calculated the total number of miles. That was 318. So we're just going to plug that in, 318. And the total number of days, we already calculated that as well. That is 4 days. Keep my units here. Now, I divide 318 by 4. And that gives me 79.5 miles per 1 day. That's my rate. Okay, so you just need to identify what two quantities they want in a ratio, and then plug those quantities in. By the time you get to the end of your rate, you know, especially with stuff like this, it's nice to have a 1 in the denominator. You don't necessarily have to, but you know, for things like this, at least, it's nice to have that 1 there. Okay, so let's do another example. This time we're talking about transportation. So, an Atlantic City Express bus makes regular trips between Paramus and Atlantic City, New Jersey. At 6:00 p.m., the bus is at mileage marker 40 on the Golden State Parkway. At 8:00 p.m., it is at marker 170. Find the average speed of the bus. So, what they want, as you can see right down here, they want the average speed, right, which is in miles per hour, as usual, right? So, miles over hours. How many miles did we travel? Well, we ended at 170 and we started at 40. That means we traveled 170 minus 40 hours. All right, our time we spent traveling, well, that was 8 o'clock p.m. to 6 o'clock p.m. Sorry, 6 to 8 p.m. Right, so we started at 6, ended at 8. So to calculate that, we say 8 minus 6. Whoops, I mislabeled my hours. Hopefully you guys caught that. This should have been miles, and this is hours. All right, so now I just do I do my little calculation here. So 170 minus 40, that is equal to 130 miles for every 2 hours. Now I need to do my last calculation because I like my numbers in my denominator to be 1. So I'm going to cut that 130 in half, and I'm going to end up with 65. So I have 65 miles per hour. And that's how you solve that guy. Okay. So what does it mean when we visualize rates? Well, we went over earlier sort of the steepness of any graph is related to its rate. When we visually represent rates, it tends to be sort of a rule, unless it's otherwise stated, that whatever is in the denominator goes on the vertical axis, and whatever is in the, sorry, this one's the numerator. Whatever's in the numerator goes on the vertical axis, and whatever's in the denominator on the bottom here goes on the horizontal axis. All right, so that's just a little rule to remember. All right, so let's go ahead and do another example. So suppose we are dealing with some library holdings here. So in 2011, the U.S. public libraries spent an average of 40 cents per capita on electronic materials. Here, per capita means per person living in the library's legal service area. This amount was increasing at a rate of 50 cents per year. Draw a graph to represent this information. Okay, so let's go ahead and highlight some stuff. So in 2011, 40 cents per capita on electric materials. Okay, so that was their initial rate. Okay, they give us a bunch of background. And then they say this amount was increasing at a rate of 50 cents per year. So it started at 40 cents, then it increased at a rate of 50 cents per year. All right, so they're asking us to draw a graph to represent this information. So first thing, let me just figure out what they're asking us to graph, right? Because they give a couple of different rates here. The first rate they give is 40 cents per capita on electric materials. The second rate they give us is 50 cents per year. That's what the amount is increasing. Right. So since this doesn't talk about the number of people increasing, right, the per capita stays the same basically, which means that our rate that we're going to be dealing with is going to be in dollars per year, right? So dollars per year, right? Our initial point is going to be 0.4 per year. That is our initial. Okay, so let's go ahead and make our axes, and then we're going to deal with our points. So pretend that these are super straight and in a right angle. And then I'm going to go ahead, since this increases at 50 cents per year, I'm going to do my tick marks. I'm going to scale them to 0.5 each, and we'll just call this dollars. So I have $0.5, $1, $1.5, $2, 2.5, and so on and so forth. Now on the bottom, right, this is dollars, and on the bottom I'm going to put years. All right, this is because years is in the denominator and dollars is in the numerator. That's why I'm arranging it like this. So the years starts in 2011. We could certainly choose to start our years at year 1 if we wanted to, but sometimes with dates like this, it's easier to start at the actual year, and that's just so that you can recognize it on the graph. So we're going to make our first tick mark way over here at 2011, 2012, 2013, blah, 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 2014. Okay, and if you want to, this is just a matter of personal choice. I chose to make 2011 the first tick mark out. If you wanted to, you could make it right at the origin here. It doesn't, you know, just as long as you're clear about what you're labeling. So at the very first year, at 2011, we had a 0.4 initial cost. So at 2011, our dollars per year was at 0.4. We're going to label that 0.4 2011. Okay, so now if we just if we think about the next year out with this one, since they're adding 50 cents per year, right, we can sort of figure out what the next year is going to be. So 2011 0.4. 2012 is going to be 0.4 plus 0.5, right? Because it's per year we gain 50 cents. 2013 is equal to 0.4 plus the 0.5 from 2012 plus another 0.5 from 2013. 2014 is going to equal 0.4 plus a 0.5 from 2012 plus a 0.5 from 2013 plus a new 0.5 from 2014. So this is going to give us, of course, 0.4. This will give us 0.9. This will give us 1.4. And this one's going to give us 1.9. And so we may not have noticed it, but we've created a bunch of ordered pairs here that we can graph, right? Since this is all values along my x-axis, these are their corresponding values along the y-axis, right? So my ordered pairs are just 2011, comma, 0.4. We already graphed that one. 2012, comma, 0.9. We haven't graphed that one yet. Let's just graph it. 2012, we'll say 0.9, somewhere right around there. 2013, 1.4. Okay, 2013, go up to, let's say that's roughly 1.4. All right, and then 2014, 1.9. Roughly there. Okay, so now I've created 4 different points, which is a little overboard. All we really need is 3, but that's fine to do 4. There's no problem with that at all. So now we just connect them using some points. Sorry, using a line. So I draw a line through all my points, and that is it. Notice that I did not draw an arrow to the left, extending it beyond infinity, because we don't know what the data was during that time. That would be a big guess for us to say, well, it continues this trend. Because, hey, and if it continued this trend in 2010, we'd actually be getting paid for the wireless service, which is, it doesn't make a whole lot of sense. All right, so that is another example. Let's go ahead and do, this is the last example. So this example says, Nadia prepared the following graph from data collected on a recent day at a local bank. So first they want to know, what can we determine from this graph? Second, they want to know, what's the rate of this graph? So they say, number of transactions, time of day. Right? So as you can see, So I guess this first question is kind of asking us, like, what is the very basic material that we get out of this graph? Not really how can we interpret this graph, because there's not a whole lot to interpret. So they say, what rate can be determined from the graph? Well, the rate, since the vertical is number of transactions, that goes in the numerator. And the time of day is in the denominator, and it does look like it's in hourly increments, and so we say per hour. Number of transactions. We can just kind of scribble out this one, actually, because transactions over hours. All right, so part B. Part B, they ask us, what is that rate? So we have to figure out, what is the rate? What is the slope of this line? How many transactions per hour are they getting? Well, let's take a look. So let's analyze this first point. This first point says at the 9 o'clock hour, they had 75 transactions, right? So let's see now. Time of day is on the bottom, so it's in the X position. So we have 9 o'clock and 75, right? That's 1 point on the graph. Here's another point. So this says that at 11 o'clock, we had 250 transactions. So 11 o'clock, comma, 250. And this wants us to know the rate per hour that this is happening. So what we need to do is we need to identify that, right? So transactions over hours is what we want to calculate. So first, I'm going to say how many transactions happened in this interval of time. I started at 75 transactions, and I ended at 250 transactions. So the number of transactions is going to be 250 minus 75. As far as hours go, I started at 9 o'clock and I ended at 11 o'clock. So the number of hours that this happened over is 11 minus 9. I'm going to keep my units here. Let's say TR for transactions. And then HRS. Okay, so now I do my addition, right? I subtract 75 from 250, and I believe I get 175. And then I have 11 minus 9 hours. That gives me 2 hours. 175 transactions for every 2 hours. So, interesting. So that, now we're just going to divide it and give the decimal form, right? So 175 divided by 2. That gives us 87.5. So it's 87.5 transactions, TR, per 1 hour. And that's our final rate. Oh, I screwed up my numbers on this. I was thinking that did not look correct. So something that I screwed up on here, when I identified my second point, I identified the Y point as 250. If you look closely at the graph, this is in 25-point increments, right? 150, 175, 200. This should be 225. Let's redo that. Let's redo that and find out what the real rate is. I thought that looked a little strange. Okay, so the 75 stays. We turn this 250 into a 225. So 225, 225. Okay, so that would mean that all these calculations are a little bit different. So now, 225 minus 75, that gives me 150. That's looking a little closer to what I thought it was. Now, when we do the division of 150 over 2, we get 75. Oh, that's not correct. We get 75 transactions per hour, and that's more like it, right? And we can see that from the graph. You know, I mean, we can just kind of notice that this must be 8 o'clock right here, and it started at 0 when they opened at 8, right? And it ended up at 75 at 9 o'clock. That's a pretty good indicator we're moving at 75 transactions per hour. When I pulled up that 80 number, I was thinking, that's not really what I saw from the graph, so maybe I should make sure that I did everything correctly. And it turns out I didn't. Big surprise. So that's about it. That'll be our lecture for Thursday, and I'll see you guys all in class again on Tuesday. Make sure that you guys study this stuff. Make sure that you're comfortable with brute force stuff. Yeah, make sure that you know what the intercepts are. Make sure you know how to find those, because we're going to go into some better graphing stuff the next time we meet up. So all you guys, I hope you have a great weekend, and we'll see you in class.